My name is Ryan Norris. I work at Pratt & Whitney in the Materials and Process Engineering group. Today we're talking about potential industry standards for microtexture characterization primarily. That's a terrible title. Oof. It didn't look like that when I sent it over. But we're talking about microtexture. As some other guys pointed to some EBSD and some data there. But how do you quantify that data? How do we use that for design? And incorporate that into our design spaces for parts that do eventually fail from microtexture in the field. So it's been a problem for maybe 2 decades, funded by the Air Force, tackled by all the OEMs. So it's a critical problem. We need a way to kind of speak the same language, and that's kind of what this approach is going towards. So I'll go briefly over the background of titanium, some cold dwell fatigue and microtexture mechanisms, some of the processing effects on what drives microtexture changes, microstructure, how do we quantify it currently, today, and then what are we going to do in the future state, and even some longer term methods that are further down the line. So I think it goes without saying titanium is workhorse in the aerospace industry. I think at least the 4,000 engines, there are at least 20 to 30% titanium. So we have 6.4, 6.242, 6.246. There's IMI 834, alloy C. It's kind of everywhere in the engines. For most part, for microtexture, cold dwell fatigue, we're kind of they call it cold dwell fatigue because we're kind of in the front of the engine, below maybe 400 or 500 degrees F. That's kind of the regime in which this mechanism kind of is active. So it's our fan blades, our fan hubs, critical parts that if they fail during service, the airplanes can be coming down. So it's a critical life-limiting part for safety. And so what we're looking at really is how do we quantify microtexture? And some of these images here, they're colorful for us. And I will say that microtexture is not what's flying in our parts, just for visualization. That's pretty bad. But how do we quantify these types of colorful images based on the orientations of these crystals? And then how do we use that kind of to communicate that to requirements for suppliers and across the industry, so we're all speaking the same language. We can have billets with the same microtexture requirements, work to the same type of problem. So a little more background. OEM is orientation imaging microscopy. That's what we usually collect to get this EBSD data, electron backscatter diffraction. And what you'll get is kind of colorful images on the bottom left. And if you can imagine, each pixel here is essentially an orientation from an individual crystal. And it's difficult to see, but the plot in the middle right there is a hexagonal crystal. And if you're looking down the North Pole of that little hemisphere, you're going to see you're basically looking straight down the axis of this hexagonal crystal. And it'll be red in a 001 IPF image on the left. Versus if it's on its side, it may be blue or green or something like that. And it's really these combinations of hard-soft due to the anisotropic properties of titanium, inelastic incompatibilities between the hard and soft. They generate basically kind of a stress concentration at these interfaces of these hard grains, and it'll lead to essentially a significant dwell shift compared to your continuous LCF life. And it's a creep mechanism. The creep mechanism is time dependent, and you'll see basically that the magnitude of dwell shift for 6.4 is going to be maybe 2 to 5 to 10x. It's been reported for 6.242, another dwell sensitive alloy, to be up to 20x depending on the level of microtexture in your parts. So it's a significant problem if you're designing to LCF and you have now a 10x shift. That can be very significant as far as the lifing the parts. So what we need here is how do we quantify the image on the left? It's easy maybe visually to say, yeah, it looks bad or good, but how good is it quantitatively? And so that people analyzing the same image will get the same answer or close enough. So as everyone knows, microtexture is not random. It's all processing dependent, time dependent from the history, the thermal history, the mechanical history of the parts. Starting with the ingot breakdown and cogging process, there's opportunities to improve microtexture there. In the alpha beta working stage, during the beta quench, once you have the kind of billet, 12 or 10 or 14-inch billet, the forging process itself is also significant in reducing the level of microtexture to a more randomized material. And heat treat, I'm not sure it's particularly affecting texture at that point. It seems to be set, but it can certainly affect your microstructure, as you see on the bottom, on the top there. On the bottom to the right, you have kind of different volume fractions, different sizes of primary alpha based on the cooling rates. And up top, you have different levels of microtexture, particularly really bad on the left, and some or others are kind of that gray area of, you know, how good is it. But I think we all say that the left one is probably the worst from inhomogeneity standpoint. And what all these different properties, different location-specific properties, they give you essentially a variation in your properties for that component flying around. And it has a full distribution, but if you're able to locate the specific properties at different locations, you'll see that, you know, there's maybe a couple different probability distributions underneath that one, explaining the variation. So it's not random, but it would be nice if we can quantify that and predict it from the cogging process, from the forging process, from the heat treat. You know, what is going to be our specific microtexture, what's going to be our specific microstructure at that given point. You know the stresses that are going to be operating in the field, the temperatures. Hopefully we can use all that data to make sure these parts stay flying. So a method to quantify, it's been around for a couple years now, probably maybe 5 to 8 years. We've been using a software called Dream 3D. It was developed in collaboration with the Air Force and Ohio State, I believe. It's particularly well suited for OIM data analysis. It'll read in your raw data, whether it's ANGs or CTF files or other flavors of the file extensions. And it'll clean up your data, remove kind of low confidence EBSD data. It'll segment your pixels together, going from a pixelated, based on the way EBSD is collected. It's every step size, every 3 microns, every 5 microns. You collect a data point, and now you have this data point, you have to kind of segment all the features into individual grains, or as we'll call them, microtexture regions, MTRs. So basically the 2 key parameters here are the misalignment for the C-axis, misalignment tolerance. How aggressively do you want to group these pixels together? And then the second part is, what defines a microtexture region? Is it a square millimeter, or is it 100 microns squared? So those are flexible parameters that certainly change the metrics that you would measure. And then once you can threshold by these parameters, then you can calculate your standard size, aspect ratio, stuff you do with traditional image analysis, densities, frequencies, distances between hard, soft kind of combinations. So you can collect all this data. Right now we have a Dream 3D pipeline. It's not available here, but we would be, I think, happy to share this type of data, this pipeline with Dream 3D, and discuss, because ultimately we would like to be able to speak the same language. If you guys have the same data, we should be able to generate the same metrics and compare it. So we would be able to share this eventually if there's interest. And with these data, now you can do more quantitative A/B comparisons, quality control, looking for defects, tails in the distributions, life assessments, etc. And you'll get all these features as a function of, we'll call MTR class, which is hard, which are features that are aligned with your particular stress axis. Soft, which are kind of 90 degrees or so. Initiators, it's a term by the Air Force, but that's also kind of just 45 degrees off your stress axis. So here's just an example. You start with kind of raw data on your left. Dream 3D will read that in. It's pretty quick. I mean, these scans are usually, we've been collecting 10 by 10 millimeters at a 3 micron step size, which it's a fairly large data file, about 10 million pixels. And we're usually trying to characterize the tails or the sizes, the average sizes of these features. MTR is different. And you might look at, so we'll segment them into the cleaned up data, and then we'll actually just look at just the MTRs only. And we'll collect the sizes. You can look at different pedigrees of material, different heat codes, different locations, hard, soft, MTR sizes, etc. You can look at histograms. If you want to go more probability distributions, you can look at There is 3 points, 3 curves on that probability plot. But we're looking at max size as a function of, what is the size of your scan, and it's essentially saying that the probability of finding these big, kind of aggressive regions gets higher when you collect more data. So stuff like I think AOT and other methods are trying to go for like large area scans much quicker than EBSD can, so we can find these types of features, which are very rare. They're flying around, but they're just maybe not in the high stress locations. So it's rare that they fail from them, but they are flying, and we would like to know how frequent they are actually out there. So Dream3D really enables this type of statistical analysis comparison of microtexture. Versus before 5 years ago, where it's really just qualitative assessment, which is this looks bad, this looks good, and that's really not acceptable in this day and age. So the other thing, so we talked about those two key parameters, this orientation tolerance, how aggressively you want to group the pixels, and the minimum size. So if you vary those two, what would your output look like for this one sample? And you can see. You can make MTRs disappear, or you can make it pretty much be 100% MTRs for this one particular dwell sample. And so that's really, the Dream3D pipeline is there, but we need to be able to, as an industry, say, this is what an MTR is, this is how we group the pixels, and it's going to be one of these pictures, not whatever the person feels like typing for that day. So it's a lot of variability. We just need to be able to have industry standards to be able to compare results on an apples-to-apples basis. So future state, this is kind of going on right now with a lot of there's programs called Materials Metals Affordability Initiatives, MAI, sponsored by the Air Force, and a lot of OEMs and suppliers are part of it. So a lot of this work is from those programs where we're trying to model microtexture from the billet stage, from the cogging. Then you forge it into a component, and then you take dwell samples in different orientations, axial, radial, tangential. And they'll all have different textures. There are different locations that have different cooling rates, so we're trying to predict basically the microtexture in those locations as a function of your kind of strain maps and predicted cooling rates. So in the upper right, you kind of see a deform simulation for a kind of a simple pancake upset forging model. And you'll see the high strain kind of forms that nice band in the middle, and you'll see that the microtexture is essentially non-existent in the regions of high strain. So there's certainly a correlation between how do you make the material and what's the microtexture going to be in at these given locations. And you can then, with knowledge of your billet and your forging process, you can now predict what microtexture will be in this given spot. Is it detrimental? Do we have to add more forging strain? Do we have to give it a faster cooling rate to give it better tensile properties? So ideally it's part of the kind of ICME approach that we've been working towards under these MAI programs. And this is a terrible slide, got jumbled, but this is near dear to my heart. Even further down the road, we're trying to develop methods that are scalable to the level of data that's being collected. We have now automated scopes collecting gigabytes of microstroke optical images in a day. We would normally produce image analysis, segment the images, get the primary alpha grain sizes, volume fractions, and they do that, and it's about 5 to 10 images a day, or maybe 20, 30, 40 images, but it's not scalable. If you have now 1,000 images, go do image analysis, it's going to take them a week, and for us, we usually need answers quicker than that. So we're looking at different techniques in the future that would be scalable, repeatable, transferable, and preferably don't require us to specify upfront what you actually care about in that image. So we do the segmentation for grains. We know we want the grain sizes, we want the volume fractions. But what if that doesn't correlate, those metrics don't correlate with whatever fatigue property you're trying to capture or predict? So we've been using actually image recognition so there's machine learning for facial recognition, applying it to microstructures. And it can recognize microstructures very easily. And you'll see across for various pedigrees of Ti-64, different volume fractions, different cooling rates, all different heat treats. You'll see they cluster in just 2 dimensions. You'll see they cluster pretty nicely in the middle plot there. So you can say, given any new image, what is it closest to? What is the heat treat that this material probably had received? Are the outliers? And so not just classification, but you can also predict properties pretty well for fatigue and tensile. We also use it for EBSD, predicting dwell fatigue life from EBSD maps instead of doing all the quantification that I just showed you. So these methods are very fast, they're flexible, they're, I think, very powerful. I think we'll see a lot more of them in the future. They can also perform the same types of segmentation, albeit much faster than we typically do with standard software. So it's an exciting field. I think we'll see a lot more there. We'll try to keep presenting current status on there. But it's already popping up in different softwares, AI. We'll see it more, and we'll see how it impacts us. So I say this method, it is developed. It's always improving, but there is a method, Dream3D pipeline today, that exists. That's used by TimeMat. Rolls-Royce has a GE, Pratt and Whitney, Wyman Gordon. These folks do have it and have used it successfully. So it's already got a foothold, I'd say. There's been positive feedback as far as, this is how we qualify bill approval process. We're going to change the route, the cogging process, or the ingot melting process. And we want to quantify, verify there's no microtexture changes in the final product. So we're doing that today with various suppliers, TimeMat. This has potential to be an industry standard, so we're still working on that. And as designs and titanium gets pushed to more demanding applications, as we're trying to squeak out every last percentage of performance in our engines, that usually drives stresses up, temperatures up, stress the volumes of your parts up if the max stress doesn't go up. So we need to be able to control microstructure more than we are today. And I'd say we are pretty loose on microtexture and microstructure standards. So that'll be something going forward to make sure our parts are safe and we're all have dependable engines. So just a few acknowledgments, the US Air Force and the MAI programs. Most of this work came from the PW9 team here, which is probably a lot of the folks at this conference. So without them, this work wouldn't be possible.